The most advanced factories on Earth don't use steel or robots. They use DNA. When we imagine factories, we picture assembly lines, robotic arms, sparks, heat, and noise. Vast buildings where raw materials go in one end and finished products come out the other. But the most sophisticated factories humanity has ever encountered aren't large at all. They're microscopic. Every living cell on Earth is a fully automated manufacturing plant, capable of assembling complex machines atom by atom, repairing itself, copying its own blueprints, and running continuously for decades. Life isn't just chemistry, it's industrial chemistry, refined by billions of years of evolution. Cells take simple molecules from their environment and transform them into proteins, membranes, motors, sensors, and structural components, all at room temperature with astonishing efficiency. They recycle nearly everything, they correct errors, they self-assemble without centralized control, and in multicellular organisms, trillions of these factories coordinate to build brains, bodies, and ecosystems. That matters a lot because it means that the molecular industry isn't speculative, it already works. The real question is whether we can generalize it, taking principles life uses and applying them beyond biology, to manufacturing, medicine, infrastructure, and eventually civilization itself. In this episode, we're moving past the old science fiction image of swarms of tiny robots and into something more realistic and more powerful. Factories made of molecules, often built from DNA, operating as programmable assembly lines at the smallest scales. Not single machines that do all the jobs, but whole ecosystems of specialized builders. And not machines that imitate life, but machines that learn from it. Nature already solved molecular manufacturing. If molecular industry sounds exotic, it's only because we don't usually describe biology in industrial terms. But every cell is packed with machines, not metaphorically, but literally. Ribosomes function as automated assembly lines, stitching together proteins one amino acid at a time. Enzymes act as precision tools, lowering energy barriers and ensuring reactions happen in the right order, at the right speed, with the right products, and in the right place. DNA serves triple duty. It's a blueprint, a storage medium, and a control system, regulating when and how manufacturing occurs. Messenger RNA acts like work orders, dispatched as needed. Quality control systems detect malformed proteins and recycle them. Damaged components are repaired or replaced. Even energy management is tightly controlled, using chemical gradients and molecular currencies like ATP. Most importantly, biological molecular industry is parallelized. Cells don't rely on one giant machine, they rely on millions of tiny ones operating simultaneously. That makes the system resilient, scalable, and remarkably fault-tolerant, qualities even modern industry often struggles to achieve. This is also why life can persist, adapt, and in some cases last for centuries. Aging itself is not simply a matter of wear and tear, like a machine grinding itself down. At the molecular level, most of the damage our bodies accumulate is constantly repaired. DNA is corrected, proteins are recycled, cells are replaced. What changes with age is not the existence of those repair systems, but how aggressively and accurately they are applied. In other words, aging is as much a control problem as a materials problem. Evolution optimized organisms to survive long enough to reproduce and raise offspring, not to operate indefinitely. Many repair processes are deliberately throttled back over time, or allowed to become less precise, because from an evolutionary standpoint, extended longevity offered little advantage once reproduction was complete. Nature already demonstrates that longevity is, at least in part, a manufacturing and maintenance problem. We are now beginning to see how those settings can be altered. Research into sensitive cell removal, telomere regulation, epigenetic reprogramming, and cellular quality control systems suggest that many aspects of aging are not inevitable failures, but programmable limits. They are rules written into biological machinery, not hard physical constraints. Molecular industry does not promise immortality, but does point towards something more realistic: continuous repair, targeted intervention, and the ability to keep biological systems operating far closer to their optimal state, for far longer than evolution ever required. Understanding cells as factories reframes molecular industry entirely. We are not inventing something new. We are attempting to take the most successful manufacturing system in the known universe and make it programmable beyond biology. what molecular industry actually means. When people hear nanotechnology, they often imagine tiny mechanical robots crawling around like ants, building objects atom by atom. That image is memorable and mostly wrong. Real molecular industry is less about free-roaming machines and more about structured, constrained, and highly specialized systems. At the molecular scale, randomness dominates. Thermal motion jostles everything constantly, a phenomenon known as Brownian motion. So instead of fighting the chaos, molecular manufacturing uses it through what is called the ratchet effect. Molecular machines don't push objects like macro-scale robotic arms. Instead, they use chemical energy to act as a one-way gate. When a random thermal jiggle moves a component forward into the correct place, the machine clicks into place, preventing it from moving backward. Components fall into correct configurations because the system is designed to make the wrong ones energetically unstable, while ratcheting the right ones toward assembly. Modern approaches fall into three broad categories. There's wet nanotechnology, which uses biological or bio-inspired systems in liquid environments, enzymes, proteins, and DNA-based machines. Then there's dry nanotechnology, involving solid-state systems, surfaces, and atomic-scale fabrication. And there are hybrid systems that combine biological scaffolds with non-biological materials. What unites them is the factory metaphor. Molecular industry does not mean independent nanobots. Tiny, all-purpose self-alchemy machines are likely less effective than something better resembling an ecosystem or economy, and hard to keep from overrunning us in some gray goo or green goo scenario. So molecular industry means assembly lines made of molecules, often anchored to membranes, channels, or scaffolds, where inputs flow in, products flow out, and every step is tightly controlled. This distinction matters especially for safety. Molecular industry works best when it's embedded, localized, and dependent on specific environments, exactly how biology already keeps itself in check. DNA as a construction material, not just code. DNA is usually described as information, but from an engineering perspective, it's also an extraordinary building material. DNA strands bind in predictable ways and fold reliably into specific shapes with nanometer precision, a technique known as DNA origami. However, we are not limited to the four natural bases of A, T, C, and G. Modern ZNA, or xenonucleic acids, let us build even more durable, non-biological structures. By using synthetic backbones, we can create molecular jigs and scaffolds that are functionally invisible to natural biology. These ZNA structures are incredibly stable because natural enzymes don't recognize them, meaning they can't be accidentally eaten or degraded by the very cells they are meant to repair. By designing sequences carefully, researchers can create molecular scaffolds that position other components exactly where they're needed. Proteins, enzymes, metal nanoparticles, even semiconductor elements can be arranged using DNA as a molecular jig. Once assembly is complete, the DNA can remain as part of the structure, or be removed entirely, and the equivalent of cyborg DNA or cyborg cells is definitely on the table, things grafted of biology and more traditionally metal mechanics. But even regular but controlled biological microindustry capability will be amazing, especially powerful for medicine. DNA scaffolds can organize repair enzymes near damaged tissues, guide molecular machines to specific cells, or create localized factories that manufacture therapeutic compounds inside the body. Instead of flooding the bloodstream with drugs, molecular industry provides targeted on-site production. More broadly, DNA's real value is not strength, it's programmability. It allows molecular factories to be reconfigured without rebuilding them from scratch. Change the sequence and you change the machine. In that sense, DNA isn't just a blueprint, it's the tooling system for the smallest factories imaginable. Molecular assembly lines. At the molecular scale, manufacturing doesn't look like machining, it looks like chemistry in motion. Instead of robotic arms and conveyor belts, molecular industry relies on reaction pathways, binding sites, and controlled environments that guide matter through a sequence of transformations. Ribosomes are the clearest example. The ribosome is a molecular scale factory found inside every living cell, built from RNA and proteins, and its sole job is to manufacture other proteins. It doesn't do this by grabbing parts and snapping together like a robotic arm. Instead, it works more like a programmable assembly line. A strand of messenger RNA feeds through the ribosome like a punch tape or digital instruction stream, and the ribosome reads it one step at a time. As the instructions pass through, the ribosome pulls in the raw molecular building blocks, amino acids, from its surroundings and joins them together in a precise sequence. Each step is checked for alignment and chemical compatibility before the next one proceeds. If the instructions do not match, the process stalls or aborts. The result is a finished protein folded in the correct order, produced reliably billions of times per day across the living organism. Enzyme cascades operate on similar principles. Instead of one machine doing everything, intermediate products are passed from one molecular station to the next, ensuring reactions happen in the correct order, at the correct time, and under controlled conditions. Together, these systems show that life doesn't rely on kinetic chemistry, it relies on disciplined industrial-scale molecular manufacturing. Future molecular factories would operate the same way. Feedstock molecules enter a controlled space. They are modified, combined, folded, or assembled in stages. Each step is simple. The complexity emerges from scale and parallelism. Instead of one assembly line making 1 million products, you have 1 million assembly lines, each making one. This is especially powerful for medicine. Repairing tissue, correcting DNA damage, or maintaining cellular health does not require large interventions. It requires continuous, localized maintenance. Molecular assembly lines embedded in cells or tissues could replace damaged proteins, clear harmful byproducts, or rebuild structures faster than aging degrades them. Crucially, molecular industry scales sideways, not upward. You don't build bigger machines, you build more of them. That makes these systems inherently resilient. If some fail, others keep working. If conditions change, the systems adapt rather than collapse. In this sense, molecular assembly lines blur the line between manufacturing and metabolism. They aren't just factories that make things, they are processes that maintain systems over time, which is exactly what long-lived organisms need. Energy, feedstock, and waste at the molecular scale. Every factory needs power, materials, and waste management. Molecular industry handles all three, very differently from traditional manufacturing and far more efficiently. Instead of electricity driving motors, molecular factories use chemical energy gradients, light electric fields, or thermal differences. Biology already demonstrates this with ATP, proton gradients, and photosynthesis. Artificial systems can use similar principles, converting energy directly into chemical work without intermediate steps that waste heat. Feedstock requirements are minimal: carbon, hydrogen, oxygen, nitrogen, phosphorus, the same basic ingredients life already uses. These are enough to build staggering complexity. These elements are abundant on Earth, common in space, and easily recyclable. A molecular factory doesn't need refined parts from afar, it needs atoms in roughly the right ratios. Though I'll note, we could add something weird to the mix as a control element for engineered life, like it can only replicate using something pretty rare but non-toxic like zirconium or gold. And keep in mind, even if things had to be 1% gold, you'd be unlikely to have even 100 grams of them in your body. So you wouldn't need to be too worried about losing it or needing to monitor waste for recovery, though such biomachines could also be amazing in waste dumps and treatment facilities for breaking things down and recovering valuable elements. And waste too becomes a different problem. At the molecular scale, most waste is not garbage, it's misplaced material. Biological systems routinely disassemble and reuse molecules, breaking complex structures back into reusable components. Molecular industry extends this idea. Nearly everything is recyclable because everything is built from the same basic pieces. For medicine and life extension, this is transformative. Aging is driven in large part by accumulated molecular damage and inefficient cleanup. If molecular factories can continuously recycle damaged components and maintain cellular environments, then aging shifts from an inevitable decline to an engineering challenge. Instead of periodic repairs, health becomes maintenance, and maintenance becomes manufacturing. But molecular industry makes possible. When manufacturing operates at the molecular scale, the distinction between making, repairing, and healing begins to dissolve. Materials can be grown instead of machined, with structures optimized, protein by protein, even atom by atom for strength, flexibility, or conductivity. Infrastructure can become self-healing, repairing cracks or damage before failure occurs. Devices can adapt their properties in response to stress, temperature, or radiation. We cannot overstate how profound the implications are for medicine. Molecular industry permits in-body manufacturing, producing drugs, enzymes, or structural components exactly where they're needed in exactly the right amounts. Instead of systemic treatments with broad side effects, therapies become localized, responsive, and continuous. Tissues could be repaired rather than replaced. Organs could regenerate instead of failing. Fatigue poisons cleanse from your brain to enhance and augment sleep's restorative process. Cellular damage that accumulates with age, misfolded proteins, damaged mitochondria, genetic errors could be identified and corrected in real time. Life extension in this context isn't about radical redesign of the human body, it's about keeping the existing system running as designed. This does not mean immortality or instant cures or abandoning biology. It means shifting medicine from emergency intervention to industrial maintenance. Just as modern infrastructure lasts longer with regular upkeep, biological systems could remain functional far beyond their current limits. Beyond medicine, molecular industry enables closed-loop production systems that approach zero waste, making scarcity less about resources and more about access and organization. Manufacturing becomes local, adaptable, and nearly invisible, embedded into environments and systems it supports. Molecular industry in space. It wouldn't be SFIA if we didn't talk about applications for space, and we should, as space is where and when molecular industry stops being optional. Traditional manufacturing struggles off Earth because it assumes abundance of gravity, air, large machines, replacement parts, and constant resupply. Space offers none of these. Every kilogram is expensive, every failure dangerous, every resupply mission is a logistical headache. Molecular industry flips that equation. Instead of hauling finished parts across millions of kilometers, you bring recipes, catalysts, and basic feedstock. Carbon from asteroids, hydrogen from ice, nitrogen from tenuous atmospheres, all become raw material for construction. Habitats built this way won't just arrive complete, they grow, adapt, and repair themselves. Holes heal micrometeoroid damage. This leads us to the concept of biological architecture. Instead of launching completed space stations, we might instead launch a seed, a complete molecular manufacturing unit. This seed would utilize solar energy and local carbon from asteroids to grow a station, potentially even an O'Neill cylinder, over time. Probably not a quick process any more than growing a tree or a whale is. In this model, though, the line between an orbital outpost and a living organism vanishes. The habitat isn't just a place where life lives, it's a form of life itself, scaling from a small cluster to a megastructure by processing the raw materials of the cosmos. Many more options are out there, too. Radiation shielding that rearranges itself in response to solar storms. Life support systems regenerate filters, membranes, and tissues continuously. This also changes how humans survive long missions. Instead of carrying decades worth of spare parts, mechanical and biological, crews carry molecular toolkits. Something breaks, it's rebuilt, including them. If a medical problem arises, treatment is fabricated locally, tuned to the individual. Radiation and cancer concerns become a nightmare of the past. Long-duration interstellar travel becomes far more plausible when both the ship and the crew can maintain themselves indefinitely. But most importantly, every world we seek to terraform, every attempt to build a second Earth, will differ from Earth in fundamental ways. We can try to brute force the problem, forcing terrestrial ecosystems into alien environments like a square peg in a round hole. And this would work, and this is why the channel's motto is, if brute force isn't working, you're not using enough of it. But sometimes it's better to use your brains, and we can adapt life itself to fit these worlds instead, what we call bioforming. That means bioforming organisms rather than terraforming planets, and that approach, advanced genetics and molecular industry aren't just useful, they're indispensable. Civilization without factories. As molecular industry matures, the concept of factory as a place begins to disappear. Manufacturing becomes distributed, embedded into habitats, vehicles, clothing, and even ecosystems. Production happens where it's needed, when it's needed, and exactly the amount required. Large, centralized industrial zones give way to quiet, invisible production woven into daily life. This reshapes economics. Scarcity doesn't vanish entirely, but it moves upstream, away from finished goods and towards energy, computation, and governance. In a world where every kitchen or workshop has a molecular-scale 3D printer and atoms are essentially free, our entire concept of intellectual property must shift. Wealth becomes less about ownership of physical objects and more about access to the recipes that build them. The global economy would transition to a recipe economy, where the primary commodities traded are encrypted blueprints and validation codes. In this post-scarcity landscape, the value is no longer in the matter, but in the information and governance of systems that verify which molecular designs are safe, efficient, and authorized for production, not to mention fashionable and up-to-date. For post-scarcity civilizations, molecular industry provides the physical foundation, not abundance through excess, but abundance through efficiency and maintenance. Civilizations stop expanding because they must replace broken systems, and start expanding because they choose to. Even collapse becomes harder. A society that can rebuild itself at the molecular level is extraordinarily resilient. Infrastructure degrades slowly, adapts quickly, and recovers gracefully. And while I suspect otherwise, this may be one reason advanced civilizations of the universe appear quiet rather than extinct. They don't burn bright and die young, they stabilize. Risks, limits, and the control problem. Of course, molecular industry isn't magic, and it isn't risk-free. Anything capable of assembling complex structures atom by atom can also disassemble them. Errors propagate quickly. Poorly designed systems could damage ecosystems, biology, or infrastructure faster than we can react. At the extreme, uncontrolled molecular manufacturing resembles the classic gray goose scenario. Not a single runaway swarm, but a distributed failure. Control matters, safeguards matter, layered oversight, limited self-replication, and tight coupling between energy availability and manufacturing capability become essential. We have plenty of safety options, such as the gold leash we mentioned earlier, engineered machines that require trace amounts of rare elements like zirconium or gold function. Beyond elemental requirements, we can implement trophic filters. This is the idea that an industrial molecular swarm or specialized cell could be hard-coded to require a specific, non-natural synthetic molecule, a vitamin that does not exist in nature. Without a constant supply of this synthetic fuel from the factory or medical provider, the machine simply stalls and disassembles. This ensures that even in the event of a containment breach, the molecular industry can never survive in the wild or overrun natural ecosystems. There are also hard physical limits. These are not Star Trek replicators. Thermodynamics still applies. Energy still matters. Information processing is not free. Molecular industry makes many things easier, not infinite, nor super fast. Even classic nanotechnology can only replicate itself or alter its environment so quickly, and often falls slower than some classic machines can. Biological machinery will have these same limits, just as modern organisms do. In medicine and life extension, this means realism matters. Molecular repair can slow aging dramatically, but not without careful regulation. You're also not going to regrow yourself in minutes like Wolverine. Biology is complex, evolved, and occasionally fragile. Maintaining it indefinitely requires understanding, not brute force intervention. This is less a warning than a reminder. Molecular industry is powerful because it works with physical laws, not because it ignores them. This month we're talking about ocean worlds, and one of the recurring themes is that the sea is not just empty space between places that matter. On many worlds, it may be the place civilization happens. Dark, deep, pressurized, stable, and full of strange possibilities. That is also why Gods and Monsters from Curious Archive on Nebula is such a fun adventure. It explores the deep ocean as a place where real creatures and old myths start to blur together. Krakens, glowing life, giant predators, and ecosystems strange enough to make ancient sailors seem less superstitious, and more like underfunded field researchers with poor lighting. It's a good reminder that Earth already has something very close to an alien world, and Nebula is a good home for that sort of deeper, stranger science and storytelling. You also find my SFIA catalog there, including monthly exclusives, like this month's exclusive Colonizing Ocean Worlds, Subaquatic Settlements, bonus episodes, and regular episodes early and ad-free. You can use my link or the QR code to get 50% off an annual plan, or 40% off lifetime access, and it directly supports SFIA and the other creators making these shows. The long view. If industrial revolutions are defined by what they make cheap, molecular industry makes maintenance cheap. That may be its most important legacy. Civilizations that master molecular manufacturing don't just build more, they last longer. People remain healthier. Infrastructure remains functional. Habitats persist for centuries instead of decades. Space colonization shifts from heroic effort to sustainable presence. Life extension stops being a radical goal and becomes a side effect of competent engineering. Not immortality, but continuity. Not perfection, but durability. I should add that we've had some major breakthroughs in life extension fundamental research in recent months, and far more since this channel began. So while radical life extension isn't hitting the shelves this year, it's not some far future or impossible goal. In the long run, molecular industry may be less about transforming what we are and more about preserving what we already value: life, knowledge, culture, and choice, across timelines that biology alone was never meant to endure. Factories made of DNA aren't just smaller factories, they represent a different philosophy of technology, ones where production, repair, and survival are the same process. At that scale, industry stops being something humanity builds around itself and becomes something it builds into itself. And, if we get it right, the future won't be defined by what we can make, but by how long we can keep what we already have.